So far, we've seen basic mathematics of number theory, and we also saw algorithms to do computations on numbers. But to get to cryptography, there's still one element missing. We need what's called a hard problem or some computational task that we can expect or hope that adversaries will not be able to do. And we need to identify that within number theory. This is going to take a few more definitions and a few more forays into number theory. And while that may look a little complex, it's actually surprising how simple it is given what you get for it, in the sense that it's still only things from a basic algebra class, and yet it's enough to give us Diffie-Hellman key exchange and so forth. And the problem we're targeting is called the discrete log problem. So again, let's let G be an arbitrary group. We'll assume that little m is its order, and both those are known. And let's take a point or an element of the group, call it little g. And I want to define a set which consists of all the group elements obtained by raising g to powers. What are these powers? They're integers, arbitrary. And I keep raising g to them, and I get different outputs, and I collect them all. However, we did see one result which said that you never really need to consider powers which are more than the group order, because at that point you just start looping around. So I may as well restrict the powers to the range 0 through 1 less than the group order, meaning in this set. And this angle bracket around G is then shorthand for this set of powers of G. Now, as a set, it has a size, and this notation would return the size. Looking at this description, you might think that since there are m values for I, the set itself has size I, n. But that's actually the maximum size it could have. It could be smaller because maybe some of these g to the i's are the same. Mathematicians do know some facts about this set and its order. In particular, the size or order of this set is not an arbitrary number in the range of 0 through m minus 1, but is always a divisor of the group order m. Now, we overload the word order and apply it also to group elements, and in that case, it's defined to be the size of this set. That order in general could be any divisor of the group order, but we're interested in a particular case, which is that it does actually equal the group order. And if that's the case, we think of this element G as special, and we call it a generator. Sometimes it's also called a primitive element. Another way of saying that is that this set, all the powers of G, since it has size the group order, the set itself must equal the group itself. So the group can effectively be written as powers of little g. And another way of saying that is that every group element can be represented in this form or has this form for some value of I. That is, if you know that G is a generator, then every point in the group corresponds to some index, an integer I in the range here, such that raising G to the I will give you back this group element. So that's the definition of a generator. Now, if I hand you a group, there are some points in it that are generators and some not. And in fact, not every group even has a generator. Maybe some groups don't have any point that's a generator. We prefer the ones that do, and we call those cyclic. A group is cyclic if there exists at least one little g in the group which has this generator property, meaning every other point in the group can be written as a power of this generator. Now, that's quite a bunch of definitions, and as often with this number theory, it's not like any definition individually is difficult. It's just that you have to kind of go through them and stick them one on top of the other and parse. So what we'll do to help us with that is we'll look at this example. And as I kind of mentioned when starting the chapter, what we look at is the numbers 1 through 10, the fingers on our hand. And we'll discover properties of them that we may not have seen before. So mathematically, we're going to look at the group Z star 11, integers mod 11, and the multiplicative group. Since 11 is a prime, this set consists of everything from 1 through 1 less than 11, so it's actually everything from 1 through 10. The order of this group is its size, so in fact it's 10. Notice that it's 1 less than the number by which we're doing the mods. So we're working modulo 11 and the group order is 10. Now, let's take different points in the group. Let's start with 2, it's in here, and raise it to different powers with the group operation. So we're working modulo 11. Here's a bunch of possible powers, 0, 1, 2, 3, all the way up to 10. When I raise 2 to those powers, here are the things I get. 2 to the power 0 is 1, 2 to the power 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4 is 16, but remember we're working mod 11, so that gives you a 5. 2 to the power 5 is 32, and 32 mod 11 is 10, because one simple way to see it is 33 is a multiple of 11, and that's effectively negative 1 mod 11. Now, as you can see, it's getting a little harder to compute these powers. So is there some trick we could use? Yes, the answer is that all you have to do is notice that 2 to the power I plus 1 is 2 times 2 to the I. So in other words, to go from, say, here to here, you take this and you double it. So 5 times 2 is 10, 10 times 2 is 20, 20 mod 11 is 9, 9 times 2 is 18, 18 mod 11 is 7, 7 times 2 is 14, mod 11 is 3, and so forth. When you hit 10, you will notice that you get ones, but we could have predicted that because we know that anything raised to the group order will give you 1. So that was for 2. We could do it with something else. Let's take 5. It's also over here and raise it to powers. 5 to the power 0 is 1. 5 to the power 1 is 5. 5 squared is 25. And 25 mod 11 is 3. What's the shortcut this time? Well, 5 to the I plus 1 is 5 times 5 to the I. So we would multiply this by 5 to get here. So 5 times 3 is 15. 15 mod 11 is 4. 5 times 4 is 20. 20 mod 11 is 9. 5 times 9 is 45. Mod 11 is 1. At this point, it gets even easier. Since you know that the result here depends only on this, and you see a 1 here, you know it's just going to repeat. So you get the sequence over here. All right, so we've raised things to powers. And remember that by definition, this set, angle brackets around some group element, is all the possible powers of that thing. So the powers of 2 are everything that appears over here. And I put them in order. There's a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all the numbers from 1 through 10 are in that row. For 5, everything in this row. So 1, 5, 3, 4, 9, and it's sorted over here. Now we can ask about things being generators. Is 2 a generator of the group? Yes, because this set is everything in the group. It equals the set over here. Is 5 a generator? No, because this set does not equal this set. Is the group ZC star 11 cyclic? Yes, because we found a generator. Does it matter for that 5 was not a generator? No, it's irrelevant. As long as we have one generator, we have a cyclic group. Now, we are ready to define the hard operation I talked about, it turns out to just be the reverse of exponentiation. We again have our group and it has order m, and I'll now assume the group is cyclic. Remember what that means is the group equals the things you get by raising this little g to powers. So this is a succinct way of saying G is a cyclic group with generator little g. And M is the order of the group. By definition of the cyclicity and of G being a generator, if I take any point A in the group, I know that there's some unique exponent I such that G to the I gives you back A. It's unique as long as you confine it to this range. This range is everything from 0 up to 1 less than the group order. Now I will refer to this unique I as the discrete logarithm of this group element to our base G. And this will be the notation for it. The discrete logarithm is in the group G relative to the generator little g, and it's applied to the value A or the group element A. And what it does is it computes the index I such that this equation is true. It's a well-defined mathematical function. One way to get some intuition about it is to see that it's the reverse of exponentiation. How is that? If I start with some integer I and raise g to that power, I get a group element. Suppose I ask you what's the discrete log of that? Well, you're just asking, when does this g to the I equal some g to the I? Well, obviously, you've been given the I value, so it will just return that exponent. Conversely, if I raise g to the power the discrete log of A, what I'm doing is I'm saying the discrete log of A is this I. So what is g to the power that? Well, you're back to A. So this will just equal A. So these two are inverses of each other. All right, so let's get a little practice with discrete logs. And again, we'll work with our group of integers mod 11. And we know that's the numbers 1 through 10. It's a cyclic group. It has order 10. We already saw that the number 2 was a generator. So the discrete log of some group element A is by definition that exponent to which 2 must be raised to get back A. And you're working modulo 11 when you do that. Okay. So again, the discrete log of A says, to what power I do I need to raise 2 to get back A? Why 2? Because that's what's over here. Why 11? Because we're working in this group, which is Z star 11. So here I've just rewritten the table of raising 2 to different powers. So these are all the different powers. This is what you get by 2 raised to them. And now suppose I ask, if I go into the group and the group elements, which are these 1 through 10, can you compute their discrete logs? A little detail, notice that the A's here go 1 through 10, the I's here go 0 through 9. Okay, that's because these are exponents and these are group elements. But anyway, how would you compute their discrete logs? Well, you could try to use the formula. I have to see to what power to raise 2 mod 11 to get back A. And then notice that the table helps you do that. So for example, to what power do I have to raise 2 to get back 1? Well, according to this, 0. To what power do I have to raise 2 to get back 2? Well, 1. What about to get back 3? Well, it's 8. And so we see that all we're really doing in computing discrete log is writing this table backwards. And so that's what we would get, right? You see that over here, we're just saying for anything, say 6, you index into here, look for a 6, and whatever is above it is what goes here. And that's the sort of intuitive way of seeing how discrete logs work. All right, so now we know what they are, but that doesn't mean they're out there. When we want to do cryptography, we need to find groups in which we have the cyclic property so that there are generators, and we can work with the discrete log problem. Finding these groups needn't be easy, but there are some mathematical facts which help us, particularly because in cryptography, they need to be very large, and that makes things a little more challenging. So the first mathematical fact generalizes what we saw in the sense that we said Z star 11 is cyclic, and we noticed that 11 was prime. That wasn't a coincidence. Anytime you have a prime and you look at Z star P, it's going to be cyclic. We won't prove that, but that's a fact we can use. There are other facts which we may not rely on much, but may be worth knowing. No matter what group you have, if you compute its order and find the order is a prime number, then that group is automatically cyclic. Now, one thing that may be confusing is that the second fact is not implying or generalizing the first one. They're quite different. Why is that? Well, what is the order of ZP star? Well, when P is a prime, everything in the range 1 through P minus 1 has no common divisor with P. And so the size of ZP star, or if you like, phi of P, is in fact P minus 1. And in particular, that's not a prime because P is usually odd, and so P minus 1 is even. And so this is not the fact that yields this one, rather it's just a fact by itself. This is worth emphasizing again, that the order or size of ZP star is not P, it's P minus 1. There's one less thing than what you're modding with. All right. So we now have this discrete log function, and our hope is going to be to build cryptography by setting things up so that adversaries are forced with trying to compute the discrete log to break our system. And that's what the Diffie-Hellman key exchange does. So we'll have to see first how to do that. But before we do that, it would be good to understand how hard it is to actually compute discrete logs. Because if it's not hard, then a system which tries to get adversaries to do that is not actually going to be secure. So as cryptographers, we kind of hope that it's going to be hard, but we better check that out. So let's try to compute discrete logs. So how do we set that up? We're given our group, we're given some generator. We know the group is cyclic with order M, and this is its generator. And all those quantities are public. Now I'm additionally given an input, which is a group element, call it big X. And what I want is to know what is the discrete logarithm of that in this group. In other words, what is the power little x to which I must raise this g to get back the big X? Okay, so I have to solve this equation for little x. And a priori, there's a very simple way to do that. Namely, why don't I just try every possible value of little x? After all, I know that one such will exist, and its range is from 0 through 1 less than the group order. So I can cycle through all of them, and every time I have a candidate, I raise g to that power and test if I get back big X. And at some point, of course, I will. I also know that this operation, raising g to this power, is quite fast and easy to do using my exponentiation algorithms. So this algorithm actually works. So why are we saying it's hard to compute discrete logs? Well, we've kind of already seen the issue. This algorithm is much too slow. Its runtime is the number of group elements, or the order of the group, because that's the number of iterations in this loop. But we are interested in groups of order is extremely big. In particular, when the group is ZP star, the order is P minus 1, which is big O of P. And P can be as large as 2 to the power hundreds or thousands. So M then is about 2 to the hundreds or thousands, and it's extremely prohibitive to try to do this loop. So algorithmic researchers or practitioners might find this disappointing, but cryptographers like it because their viewpoint is we're going to force the adversary to compute these discrete logs. But you have to take a closer look than that because that was a very naive algorithm. And so there's still the question of, are there actually better algorithms that might run faster? And perhaps surprisingly and interesting, you can actually do much better than that naive algorithm. And there are sophisticated algorithms using more complicated number theory. And we don't go into them here, but I'll tell you what their running times look like. We see also in that space that the running times do depend on the type of group you have. The most familiar group to us would be ZP star, so integers modulo prime, and the multiplicative group. In that case, this formula tells you the running time of the best known algorithm to solve the discrete log problem. The formula is a little complicated. It's what's called a sub-exponential time algorithm. This formula gives you, this formula over here gives you the running time of the best known algorithm in what's called an elliptic curve group of order P. We're not in this class going to define how these groups work, but they are groups, and so they have, and they're cyclic ones, so you can consider discrete logs in them, and they're actually the most popular group in practice nowadays. But due to a little more math, I won't give details of those groups. Is there some way to understand these running times? Well, E here is the base of the natural log, so 2.7 or whatever, and you're raising that to a power which involves the natural log of P. When you raise e to the power log p, you just get back p. So if you were only doing that, it would be an algorithm taking p time. But the log p gets hit with the cube root, and that makes it much smaller. And so that makes this algorithm much faster than just something that has running time around p. There's also an additional term here. This algorithm is much slower because there's no cube root over here. It's just square root of p in terms of running time. So if you plug in numbers, you'll find that for small values of p, you really see an appreciable difference between these two formulas. But nonetheless, for large enough p, this gets high enough to be prohibitive. Now, there's some details that may be worth knowing in case they arise, which is that this is not true for all p. It assumes a certain structure in which the p minus 1 has as large a prime factor as possible, because the real formula depends on the largest prime factor of p minus 1. But the salient fact is that for neither problem do we know an algorithm that's what's called polynomial time, meaning runs in time a polynomial in the bit length of p. So these are the best possible algorithms, and again, their running times are actually quite slow, not as slow as the naive algorithms, but still slow that if p is large, these times are prohibitive. And that's going to be the basis of security for discrete log-based schemes. It is good to note, however, that this difficulty is conjectured in the sense that these are the best algorithms people have found. It doesn't mean that there aren't any better ones. It's just that we don't know of any at this moment. If someone were at some point to find a faster algorithm, lots of crypto would break and nothing particularly mathematical would be contradicted. That being said, I should also add that we now have quantum computers, which can make a difference here, but we'll get to that a bit later. So we gave these weird formulas earlier, but cryptographers who implement these schemes in practice want to know how fast can we compute discrete logs for primes of a certain size, because they need to pick these primes so that the discrete log problem is hard, and they want to know how many bits they have to be. People measure that through experiments. They take these algorithms and they implement them on fast computers, supercomputers, lots of parallelism, and they try to crack records. Often the way this is done is that somebody announces a challenge and gives you like a certain dollar amount to find discrete logs for primes of their challenge size. And they publish the challenge. And if you find discrete logs, you get some money. So here you can see an evolution in which the length of the prime in bits for which discrete logs was solved has been slowly going up in the community to the point where roughly by now we can do it for around 800-bit primes. For elliptic curves, it's much harder. It's since the algorithm only takes square root of p time, the best known for now is that the binary length of p is 114 is when we can crack elliptic curve discrete logs. So why would we be interested in these different kinds of groups if we do believe that, say, setting a prime to be of size maybe a few thousand in bit length will give you a hard discrete log problem? Why do we need another choice of groups such as the elliptic curve ones? The answer is that they are more efficient to work in for the protocol designers themselves or for the schemes, because you can get the same security at smaller group size. And this slide kind of goes through that computation. What it says is, suppose you have a target 80 bits of security. What we mean intuitively by that is that we want the computation of the discrete log to take about 2 to the 80 time. And now we ask, how do I pick parameters to make sure that happens? What that means is I have to look at the formulas like this one and say, at what point does its value reach 2 to the 80? And it turns out if I solve for p in that equation, the magnitude of p is about 2 to the 1024. So that tells me that I would have to take a prime p of about that size to ensure 80 bits of security for discrete log. However, if I work in an elliptic curve group of size p, then the formula is the square root of p. And so I only need to make sure that that has value 2 to the 80. And that happens when p is only 2 to the power 160. So for a much smaller p value compared to this, I have the same security. The payoff from that is that when the value of p or the size of the group is smaller, well, so is the cost for doing a group exponentiation, because that's cubic in the size of the group, which here in the log of the size of the group, which here is 160. And so roughly speaking, the ratio of these two things cubed will give you the ratio of the exponentiation costs. And so you see a really appreciable slowdown for group operations in the larger groups. And since those group operations are what we do every day for encryption, people prefer the smaller groups. As we work more with the discrete log problem, it's worth formalizing a little bit what it is. And this goes to our language of games to do that. So far, we've just said that informally, the problem is you get this input big X and find the discrete log. The formalism is more precise with regard to how that big X is chosen. So here we again fix our group. We fix its generator, and that's a cyclic group, and we know its group order, M. The game we consider is parameterized by the group and generator, and its job is to pick some group element big X and give it to the adversary. But we pick it in a very particular way, namely at random. And the way we do that is we first pick a random exponent. Remember that the exponent space is just integers in the range 0 through 1 less than the group order. These little x's are not group elements, they're just normal integers. Then we raise g to that power, and that gives us back a group element, which in this case is abstract. And that's what we hand off to the adversary. This return statement says your adversary gets that as its input. Its job is to discover the discrete log of big X, but by definition, that's just little x. So the adversary has no non-trivial oracles. It just trundles along, and eventually it says, here's my guess X prime, and it submits that as an output or calls finalize. The game just checks it. It says, okay, is X prime equal to this X? And if it is, it says, good, you won, and otherwise you didn't. And then we can look at the adversary's advantage. is going to be the probability that this game returns true, meaning it found the little x value. And the superscript tells us it's the discrete log problem. This tells us this is the group and generator. And here, of course, is our adversary. So that's just a definition, but we'll play with it at various times. We're getting closer and closer to what we started out as saying our goal is, which is to get a more detailed and complete understanding of the Diffie-Hellman key exchange protocol. And this is one more step we need to take. Namely, while discrete logs are intuitively what the adversary faces in breaking Diffie-Hellman, it's actually a little bit more than that. It's something called the computational Diffie-Hellman problem. So let's say what that is. And for that, again, we'll fix our group G with generator little g and order M. In this problem, you're again given a group element big X, which is g to the power little x. And while in the discrete log problem, that's all you were given, and you were asked to find little x, here you're also given another group element, and that's big Y, and that's g to some little y. And you aren't asked, as in discrete log, to find some exponent. Instead, you're asked to find something that's itself a group element, which is take the generator and raise it to the power of the product of these two exponents. Note that when you're trying to solve the problem, you have big X, but you're not given the little x. You just know mathematically that it exists, and similarly at this size. So you know that this is a well-defined thing, but you are not given little x and little y, so it's not clear how you're going to find this thing. So this is the computational Diffie-Hellman problem. And again, we can ask, well, if someone gave that to you, how would you solve it? Well, there is an obvious approach. Namely, we notice that we only need one of these exponents. So for example, if I can find out what this little x is, all I have to do is raise this to the power little x, and I will get this value over here. Why is that? It's g to the power little y times x, right? This equals this over here. Okay, so it's made things a little easier. I need one of the two exponents. But how do I get that? Well, by definition, I'm asking for the discrete log of big X. And so we're back to solving the discrete log problem. And if we've set up the groups right, that's not going to be so easy. So the intuition we're getting from this is due to discrete log being hard, this computational Diffie-Hellman problem is also hard. And that is somehow how we understand things. Now, it's worth being a little careful to note that it's possible that there exist clever and alternative ways to solve computational Diffie-Hellman which do not require computing discrete logs. I have no idea how that might work, but nobody has actually ruled it out. And given that nobody seems to have an approach to do that, the way we understand these two problems is as being kind of the same. We can also formalize computational Diffie-Hellman through a game. So again, we have our group G of some order M, we generate a little g, and we want to give a game which captures CDH. Again, the difference between this and the formal version is just that we are more precise about how the inputs provided to the adversary are chosen. Whereas earlier there were just some group elements, big X and big Y, here the game explicitly picks random exponents. Remember, again, this is the space of possible exponents for the group, and raises g to those powers to get the big X and big Y. And now the adversary's job is to find this quantity over here, and it submits a guess, and the game just checks if the guess is right. The game knows little x and little y, so it can, of course, compute this correctly. And the question is whether the adversary can. As usual, there'll be some advantage for our adversary, and the notation in the superscript tells you what the problem is. In the subscript, the group and generator, and the argument is the adversary. And it's the probability that the adversary finds z equaling this over here, namely the probability the game returns true. So As we develop more tools and problems in this way, it's worth exercising them again towards something that may help us both understand them and solve some problems. And for that, I'll go back to this problem of equation solving. The first example we had was solving linear equations, which is already quite useful. But here I'll go to solving quadratic or higher powered equations. So the way the setup is here is that we have our public value big N relative to which we work. It's often called a modulus. And I give you an integer e and a value in Zn. And the unknown is x, and it should satisfy this equation. Take x and raise it to the e'th power and see if you get back y. And I want you to find the x that does that. Importantly, this x has to be an integer in the range Zn, not in some other range. Okay, so if you look at that equation, how might you solve this? Well, we can use our intuition about numbers and notice that if we raise x to the e to the power 1 over e, then we would get x on this side. And so we could solve it as x is equal to y to the 1 over e. At least that's how we might approach this if we had ignored the mod n part. And if we look at that solution, it's kind of plausible, but it doesn't really fit our finite group setting because it's not clear what this 1 over e might mean. In particular, it may not be an integer. If e is, say, 2 or 3, then this is like, half or 1/3. Okay, half we might interpret it as square root, and a third is a cube root. But even those don't particularly help us in terms of computation, naively at least, over here. So, and if you think of them as fractions, it's even worse. So for example, let's say again we set the triple NEY, the given objects, to 5, 3, 2, then E would be 3. So I would be looking at Y to the 1/3, and I'm raising Y equals 2 to the 1/3. So I compute its cube root with the calculator. I would get something like this, which is wrong because it's not even an integer. But if you play around with it, you'll see there is a correct solution in this example. Can I find some integer which when cubed gives me back 2 mod 5? And the answer is 3. 3 to the power 3 is 27, and 27 mod 5 is 2. So there was a solution, just that this was not particularly the way to get it. So this gives us the approach we can use to find a solution. And this utilizes some of the group theory and algorithms we've seen. So what we're going to do is, again, not solve it always, whereas here it said that the exponent, which was given, was an arbitrary integer. I'm now going to make a relatively special assumption. Remember that our group, Zn star, has an order, which is phi of n. So in other words, this given integer big N, you can apply phi to it and get the group order out. I will ask that my exponent be in this set. And this takes a little bit of parsing and thought. Here, m, the base, is an integer. And so, of course, I'm allowed to look at Zm. And once I do that, I can put the star and say I'm looking at everything in the range 0 through m minus 1, relatively prime to m. Notice that now we have two sets or two groups that are different. This is Z star modulo n, the n over here. This says I'm working modulo a different integer, which is not n, but phi of n. Okay, so once we've gotten through all that, I claim that the way we're going to solve this equation is to take the exponent e over here and run it through a mod inverse operation inside this group. So the second argument is m to get some value d. That d can also mathematically be written as e inverse mod m. And I claim now that the solution is simply raise the y over here, to this power d that we just discovered, and you do that modulo the original n over here. So this is complicated because I'm computing D modulo the group order, and then going back to another mod, which is modulo the original n. So there are two mods modulo different things going on. Why would this work? Well, once someone gives it to you, it's actually not hard to check, right? So we're going to show that it works as follows. We're just going to compute x to the e and see we arrive at y. So let's compute x to the e mod n. Well, we know that we set x to y to the power d. So we plug that in and we get this. But now we see e times d in the exponent. And we remember one more fact, which is whenever you work in the exponents, it's implicitly or explicitly modulo the group order. So the group order here is what we call m. And I can effectively, for free, throw that into this equation. I can do a mod m here. It won't change the result. I can have it or not have it, but it's rather convenient to have it in there. Why is that? Because by definition, D is the modular inverse of E modulo M. And that means that E times D mod M is 1. And so this value is actually just 1, and so I get back y to the 1, which is y. And that says that the equation is true. So now, more intuitively, you could say, well, this D is effectively what we earlier called 1 over E, except that it's only computable under some conditions, and it is an integer, and it's done in a certain way. We could check this in our little example. Remember, we had this triple NEY, the givens of the equation, as 5, 3, and 2. If we use the method of this claim, our first step would be to compute phi of 5. So that's the size of the group Z5 star. And since 5 is a prime, the size of, remember, ZP star is always P minus 1. So this will be 4. And so N we need is actually 4. Now we notice that we can use the claim because the exponent does belong to Z star 4. Remember that this only applies if the E belongs to Z star M. And now with M equals 4, and we look at Z star 4, well, Z star 4 is what? 1 and 3, just two things, and 3 is in there. And we also notice that the value here, the 2, is in Z star 5. So we can use the method, and what it tells us to do is compute the inverse of this E value. So our E here was a 3, and we have to compute its inverse, but in what group? In this group over here, meaning working modulo 4. Oh, well, then we have to do our little searches or, brute force it. But we notice that 3 times 3 is 9, and 9 mod 4 is 1. So that means that 3 is the inverse of 3. So the modular inverse of 3 mod 4 is just 3 itself. And now we can go to the formula. It says take y, which here is 2, and raise it to d, which here is 3. So we get 2 to the power 3, which is 8. And this is all mod n, and n is 5. So we get 8 mod 5, which is 3. And that matches the sort of guess that we had computed before. So this is quite a simple tool. It's a little difficult at first glance because there's so many moving parts and different things. But once you get used to it, it's easy enough to apply. So again, we're trying to wind our way to understanding as much as possible about Diffie-Hellman key exchange. And at this point, we've understood quite a bit about its security. And we have the core of the understanding of how the protocol can function efficiently enough by the fact that we can do modular exponentiation efficiently. But if you want to actually implement this in a system, there are still a few problems to solve. And one of those is, how do we find the necessary groups? Because they have to be very large, or in other words, we need prime numbers that are very, very large. And then we need to look at the groups ZP star. And then we would even need to find generators in these groups because we need to pick this little g thing. And it's not necessarily obvious how to do that fast. So these are not actually things you necessarily have to know in a class. But one reason I like talking about them is because they make such interesting connections with classical mathematics. And you get to see these connections and how historically cryptography and computer science leverage that part of mathematics. So our first job then is to find a large prime number p, and together with it a generator g of zp star. So let's focus first on the prime. Now you might hope that there's a simple formula or prescribed way of getting primes of any desired form or size, but nobody seems to have ever found that. And so what we come down to in order to get a large prime is something fairly, you might say, dumb, which is we just keep picking numbers at random until we get a prime, and then we stop. Or what about finding generators? Once we have the prime, we know the group, it's CP star, and we need to find a generator. We saw in that little example we gave that 2 was a generator, but that needn't always be true. So how do we find one? Again, we might hope there's a formula, but in general, no one seems to know one. And the way we find generators is the same kind of dumb way. We just pick things at random from ZP star until one of them is a generator. But this idea of picking at random until you get something you like has some prerequisites to make it work. So I can pick things at random, but how do I know when I'm done? Well, I need a test for the thing I've picked being a prime. So I need to know how to test if a number is a prime. Is that all I need? No, because the other thing is that what if I keep picking at random and I just keep testing and I never find a prime because there are just not enough primes out there? So I need to know how many numbers in a given range are primes because that'll tell me the probability of success in a trial and hence how long it'll take to actually terminate. And we have analogous questions for the generators. We have to know how to test something as a generator and how many generators there are. So this just details a little bit more on the primality side. When I want to find a prime, I usually start with the desired bit length because the bit length determines security. So I might, for example, want 1024 or 2048 bit prime. Numerically, it means it's in this range, about 2 to the k minus 1 to 2 to the k. We also saw that these discrete log algorithms required that if you look at the number p modulo which you're working, it should have a large prime factor. Otherwise, discrete log isn't hard after all. And the safest way to make that happen is to just look at p minus 1 over 2. Remember, p minus 1 is even, and make sure that itself is a prime. So when people pick primes, they pick them so that this value is also a prime. So in that case, here's what our fine prime algorithm may look like. You give it the desired bit length, and it'll pick a random number in this range. And it'll test, is that number prime? And for this condition, is it also the case that this is prime? And if so, done, you output this p. If not, you go and try again. And so now our questions are more concrete, right? The primality test is a question of how these tests are done. And the question of how many numbers in a given range are prime effectively corresponds to how many iterations of this do you need. So let's look at these things in turn. At first, we look at primality testing. And this is where things get interesting with regard to mathematical connections, because this was a classical problem. It was looked at by the Greeks prior to uh, any modern number theory. And the problem is simply I give you an integer n and I ask you to output true or false depending on whether n is prime or not. And it's easy enough for small numbers like, give you an 11, it's prime and so forth. But if you ask yourself how we do it or we might do it, well, the obvious thing is, that prime means it has no divisors other than 1 in itself. So you just test divisibility. You say, I will check if does 2 divide n. If so, it's not a prime. But if 2 doesn't divide n, I can try 3. Does 3 divide n? If it does, it's not a prime, and so forth. So in other words, I compute the remainder and division of n by various candidate divisors. And anytime I get that there's no remainder, it's not a prime. If I go through all possible divisors, I can stop at root n because if there's any non-trivial divisor, there's one smaller than that. And I don't find anything that perfectly divides it, then I can say prime. So fine algorithm, but by now we've seen this enough to know what the problem is. It's slow. It takes time proportional to the square root of n over here. And our n's are of the order 2 to the 1024 or even more than that. And this would be ridiculously slow. And we've seen this story before with different conclusions. For example, when we studied exponentiation, we said, oh, it's slow in the naive way, but now wait, we can be clever and get a faster algorithm. Then we looked at discrete logs and said, oh yeah, there's this slow naive algorithm. Can we do better? And we could only do a little better. It actually is still the case that any really fast algorithm is out of reach. And primality is particularly interesting because people ask this question for a long time. And for a long time, nobody knew what's called a polynomial time algorithm, which is one whose running time is polynomial in the binary length of n. And surprisingly, around the 1960s, such an algorithm was found. But perhaps even more interesting at the time to the development of computer science and algorithms was that it was a different kind of algorithm. It was what was called a randomized algorithm. In other words, it didn't always give the right answer. With some small probability, it would give you a wrong answer. What this showed to computer scientists was that if you're willing to give up on the answer always being right, you can get substantial speed ups in algorithms. You go from an exponential time thing to a fast polynomial time thing. And that then became a paradigm in algorithms theory. And this is the kind of historical connection and evolution I was kind of alluding to when I said one reason I want to talk about this topic is exactly because of these connections. In any case, cryptographers didn't mind that there was a small error probability. They lived with that all the time. So they were able to exploit this algorithm to start building crypto systems. Now, surprisingly, the theoretical evolution didn't end there. There was still this big open question, can you actually get a polynomial time algorithm that isn't randomized? And amazingly, eventually people did. The running time has a fairly large exponent. It's now actually been reduced, but it's still polynomial, so way better than something like this, right? Because this is the binary length of n, and it's deterministic. Cryptographers don't care much about this because it's slower than this, and they don't mind the error. But theoretically, it's very interesting. So this then solves one of our two problems, which is how do you do primality testing? It turns out that the other problem, which is how many primes in a certain range, how many numbers in a certain range are prime, also has nice connections to classical number theory. So what they studied in number theory is the function pi. If you give it an integer n, it looks at the range 1 through n and counts how many primes are in that range, and it returns that. So from our perspective, you could think that we are picking a number p in the at random in 1 through n, then the probability it is prime is the number of primes in that range divided by the total number of numbers in that range. But mathematicians actually showed that this number grew at this rate. So pi of n is roughly n over log n. So the number of primes in the range 1 through n is roughly n over log n. And what's interesting about this is it's actually quite big in the sense that, so what it implies is that primes are fairly dense in the set of all numbers. In particular, if you plug that into here, the probability of picking a prime is n over log n over n, so 1 over log n. And even for n being like 2 to the power 1024, if you compute it, this probably is about 1 in 1,000. So what that says is our algorithm, which does a loop, picking numbers at random and testing primality, will maybe need 1,000 or 2,000 iterations to actually finish and find a prime. That's not too big on a modern computer. So we have set things up so we can find these groups. All right, so at that point, we've reached sort of one end point in the story, which is that if we come now back to the Diffie-Hellman secret key exchange that I showed you earlier, my hope or expectation is that a lot of it makes much more sense. And moreover, you could, for example, do something like implement it. So remember what it did. It said a large prime P and generator G of ZP star are public, and then you have the protocol steps. But now you know that ZP star is the multiplicative group mod P, and you know what a generator means. And you also know how you might find these large primes and what it means for it to be large enough, because you know how the difficulty of solving discrete logs grows with the prime size. You have ways to find these through our primality testing and random picking algorithms. So you might be able to find a good enough prime. And similar techniques, which I didn't discuss, do find generators. When you look at Alice and Bob's steps, you can somehow understand them better. Why is this ZP minus 1? Remember, P minus 1 is the order of the group ZP star. So this is picking a random exponent. And when we look now at this computation for big X, how are we going to do it? Well, it's exactly our mod X algorithm. So we have at hand a cubic time algorithm which solves the problem. So you could implement this, and similarly for Bob. When you look at the formula for computing the key, you first notice that computationally, it's again a mod X call. So again, you could do it efficiently enough if you were writing code. And also mathematically now, we see that this value, which is g to the power little x times little y modulo p, is what we call the solution to the computational Diffie-Hellman problem. And the trick is that while Alice and Bob can compute it through these formulas, because each of them has one exponent, the adversary who has neither is faced with what we call that problem, and it will have a hard time. So it's worth checking and going over that. In other words, going over the different steps of the Diffie-Hellman key exchange and seeing if you can actually answer the questions above based on your understanding.